The sole objective of this video is to prove the chain rule for multivariable functions. So loosely speaking, imagine that f is a function from Rn to Rm, and g is a function from Rm to Rq. I have a little bit more precision here about their domains. Imagine both have open domains. Say the domain for f is A and the domain for g is B. And imagine that f of A lands inside of B so that the composition g of f is well defined. Then what the chain rule tells us is that if f is differentiable at P and g is differentiable at f of P, then the new function from Rn to Rq that we form by doing g of f is differentiable at P, and moreover, its Jacobian matrix is the product of two other matrices. So the Jacobian matrix for g of f at P is the Jacobian matrix for g at f of P times the Jacobian for f at P. This is a generalization of the familiar chain rule, where you say that the derivative of a composition is the product of the individual derivatives. Here we're going to generalize that for the higher dimensional setting. So I have a different video where I talk through the chain rule and work through some examples. All we are going to do from this moment forwards is prove this statement. It's a long proof and I've broken it up into several steps. What we are going to do is show that the epsilon-delta version of the grand definition of differentiability is satisfied for this composition together with this matrix product. So in detail, suppose that epsilon is greater than 0. We are going to create a positive delta so that whenever the distance from x to p in the domain of the composition is less than delta, it follows that the composition g of f at x is really well estimated by the first order approximation centered at P, where the associated linear transformation is dg at f of P times df at P. Notice the product of those two pre-established matrices is Q by N, so dimensionally this makes sense. Our measurement here of being really well approximated is to say that the size of the error between g of f at x and the first order approximation at x is less than epsilon times the size of x minus p. So this is the epsilon-delta characterization of the limit that I typically present when we introduce the definition of differentiability. All right, we have a lot to do in this proof, so let's knock some things out right away. Some of these remarks are going to call back to earlier results. One of those results is that linear transformations do not scale in an unbounded way. So for any linear transformation, there's a positive number here called b, so that the ratio of how the linear transformation scales any vector to the original vector's length is less than or equal to b. For our purposes, we're going to say that dg at f of p is a linear transformation, so select some positive number b, so that the RQ norm of dg at f of p acting on any vector u is less than or equal to that number b times the original size of u. So that middle inequality is just based on a property of linear transformations that we proved in an earlier video. And then the last remark that I want to make right now is that since f is differentiable at p, it satisfies the epsilon-delta characterization of differentiability at p. So in particular, what I can do is find some radius delta 1 greater than 0, so that whenever any input from A is within distance delta 1 of P, then f is so well estimated at x by its first order approximation centered at P that the error between those two, f and its first order approximation, is so small that it is less than our choice of epsilon divided by 2 times this number b times the distance from x to p. Okay, let's recap. We are going to show that the composition g of f satisfies the epsilon-delta definition of differentiability with associated Jacobian matrix given by this matrix product. Along the way, we are going to need the fact that dg at f of p is a linear transformation, so we can find an upper bound for its scaling ratios. That's this fixed number capital B. Once we've identified this capital B, then we apply the epsilon-delta definition of differentiability to the function f to select the first of 3 radii that we will use to try to create a delta neighborhood around P. So our first radius, delta 1, has been chosen to satisfy the epsilon-delta definition of differentiability for f, where our notion of epsilon is actually our original epsilon divided by 2p. Okay, I hope you're with me so far because this kind of conversation is really going to be like the whole rest of the proof. It's pretty technical. On this slide, I'm just going to do some estimations to help us study this error between g of f and its first order approximation, at least what we are proposing as its first order approximation. So first thing I'm going to do is add in a fancy zero. What I do not like in the expression that we started with is this matrix product. It would be great if somehow I could break them apart. So what we're going to do is subtract and add the same term here inside of the norm, and that term is going to be dg at f of p times f of x minus f of p. This is kind of a transition from the first pair of terms to the very last term. And how you would think of it is if you grabbed that first Jacobian matrix in the product and said, okay, I know that g is differentiable at f of p, so I'm looking at like g at f of x and g at f of p, what would I like to see that matrix act on? I would like to see this linear transformation dg at f of p act on the difference between the inputs that we've already plugged into g. So that looks like f of x and f of p. So that's where you get this fancy zero from. It's trying to think like, what would I rather see? Now we really have two groups here, partly because I ran out of room and partly because the first three terms seem to be referring to the differentiability of g. But then if you look at the latter grouping of terms, there's a lot more about f there. So let's go ahead and use the triangle inequality to break these into two. The first one I'll leave as it is for now, but in the second one, notice that dg at f of p, this matrix is acting on both of the terms on the second line. So let's factor that matrix action in front and say that this second set of terms is dg at f of p acting on f of x minus f of p minus df at p acting on x minus p. Now you should be really happy with that group of terms. It is by far the best looking thing on this slide. And that's because those three terms together, f of x minus f of p minus df at p acting on x minus p, is exactly the difference between f and its first order approximation centered at p. We already know a lot about that because we know that f is differentiable at p. So those three terms feel like something that we can easily control. And then there's also something else really nice about that second set of terms, and that is that dg at f of p acting on that triple is a matrix acting on an input. And so assuming that x in A is within distance delta 1 of p, we can say that the norm of dg at f of p acting on this triple is less than or equal to that constant b that we already met times the norm of f of x minus f of p minus the Jacobian matrix df at p times the vector difference x minus p. Okay, so looking at these last two lines added together, we have two expressions here, one that looks more like it's about g, and the other one which is very clearly now about f. The second one looks beautiful, just about ready to go. Let's spend some more time with this first one. This norm isn't quite as nice as the second one, but it's still pretty good. It's a quantity that we can control because we know that g is differentiable at f of p. It needs a little bit more work, and that is because f of x has a prescribed form that really depends on f, not just on g. So if you're thinking, okay, x is going to p, f is differentiable, so it's continuous, so f of x is going to f of p, so this norm should really be like a subset of the generalized statement that we would make about differentiability for g at f of p, then you're correct. I'm just going to take you through the details about how to make that statement rigorous. All right, so here are the details. In an earlier video, we proved that differentiable functions are continuous, and they actually have a slightly stronger form of continuity than regular continuity. So we know that if f is differentiable at p, not only is it continuous at p, but it is locally Lipschitz at p. What that phrase means is that there's a positive number, capital M, and a radius which I will name delta 2, because it's the second radius we're going to draw around p, so that whenever the distance from x to p is less than delta 2 in the domain A, then it follows that the distance from f of x to f of p is less than m times x minus p. The second remark I want to make is basically saying that since g is differentiable at f of p, it satisfies the epsilon-delta characterization of differentiability. This is the characterization of differentiability that we are working with in this proof. I want to be very careful with my notation here. So we have 3 radii that we are going to define total for the domain A. The domain of G is that middle step. So I'm going to give what I would normally call delta a different Greek letter. Since G is differentiable at f of p, choose the radius sigma greater than 0. So that whenever we look at an input for G, here called y, which is within distance sigma of f of p, it follows that the distance between G and its first order approximation centered at f of p is less than what you would normally call epsilon times the distance between the 2 inputs, but here we're going to give a more specific form to that notion of epsilon. It's our original starting epsilon divided by twice the bound m from the statement number 1. So notice number 1 must come before number 2 because I need to define capital M and then choose sigma based on m. In the second step, if you compare it to the original norm at the top, we had G acting on 2 very specific inputs. One is f of p, that's okay, that's where we know G to be differentiable. And the other is f of x. With this second step, what we are trying to do is take a broader point of view. So notice here that I'm just saying any input for G, which is within distance sigma of f of p, will make this inequality true. The last thing we need to do is reassure ourselves that inputs of the form f of x can be made within distance sigma of f of p, so that this broad view in number 2 applies specifically to the norm that we have at the top. And this isn't too bad because we know that since f is differentiable, it's continuous at p. So since it is continuous at p, let's choose our third and final radius for the domain A. We'll name this delta 3. So that whenever the distance from x to p is less than delta 3, it follows through continuity that the distance from f of x to f of p is less than sigma, mapping f of x to y in the inequality in the middle of the page. So it's like this inequality that we established in step number 2 is broadly applicable. But now we are going to say we can let ourselves give this vector y the specific form of f of x. The ordering here is very important. You must first begin with 1 in order to identify the bound m that you cite in 2, and then you must do 2 in order to get this control factor sigma for the domain of G that we then make sure f is good enough for in step 3. Okay, let's put these all together. We will leave delta 1 out for just a moment. Just focusing on our conclusions on this slide. If the distance from x to p is less than the minimum of the 2 radii delta 2 and delta 3, then we can tie all of this together. We know that x is within distance delta 3 of p, so by step 3, f of x is within distance sigma of f of p. So by step 2, the norm that we are trying to assess is less than epsilon divided by twice m times the distance from f of x to f of p. But because x is also within distance delta 2 of p, bringing in our first observation, we can say that the distance from f of x to f of p is less than m times the distance from x to p, which actually leaves us with a really nice expression. So the norm at the top that we are trying to control is overall less than epsilon over 2 times the distance from x to p, so long as the distance from x to p is less than, say, both of these radii at the same time. So I said a minute ago that this is a very technical proof. At this point, we are actually done with the technicalities. We just need to tie it all together. So here is where I left off this triangle inequality argument that we were putting together. There are no words on this slide. I'm going to kind of take what we need here and put them together into a proof. So given our opening choice of epsilon greater than 0, let delta be the minimum of the 3 radii delta 1, delta 2, and delta 3. These were all radii back in the domain A, so this is a compatible computation. It makes sense to identify the set minimum. Now whenever the distance from x to p is less than this definition of delta, it follows that, and then we are looking at where we left off. So the left-hand side is the size of the error between the composition g of f and what we propose as its first order approximation centered at p. And then on the right, we had gotten there through triangle inequality, and I believe the only observation we'd really made was that linear transformations don't scale in an unbounded way. So the number b from several minutes ago was a bound on the scaling of the linear transformation dg at f of p. Okay, but now we can start bringing in the information that we get from the 3 radii. And what we concluded is that if x is within distance delta, and therefore within distance delta 2 and delta 3 of p, then that first norm is less than epsilon over 2 times the distance from x to p. Now for the second norm on the right-hand side, that is really just the ideal statement measuring the error between f of x and its first-order approximation centered at p. Going back to how we chose delta 1, we know that if x is within distance delta and therefore distance delta 1 of p, then that norm is less than epsilon over 2b times the distance from x to p. But now the b's cancel. We have twice epsilon over 2 times the distance from x to p, so we conclude that if x is suitably close to p, meaning within distance delta, then the size of the remainder, when we take g of f and we subtract off its first-order approximation with our hypothesis for the Jacobian matrix, is so small that it is less than epsilon times the distance from x to p. And this satisfies the epsilon-delta characterization of differentiability, so we actually conclude 2 things in this moment. Since we were able to satisfy the epsilon-delta definition of differentiability, we get to conclude that the composition g of f is differentiable at p. Until this moment, we didn't actually know that g of f was a differentiable function at p, but now we get that. And also, because we were able to satisfy the definition with this proposed matrix, this matrix we get out of multiplying 2 other matrices, that must be the right matrix for the associated first-order approximation. So as I tried to stress when we just talked about the chain rule and worked through several examples, the Jacobian of a composition is the composition of Jacobians. In other words, it's a matrix product. That wraps up this proof. Now, this proof is technical, but it's actually not that interesting in my opinion. It's really just a large triangle inequality argument where along the way, in order to get what we need, we bring in a lot of facts that we've already seen. Those facts included things like differentiable functions are continuous, and in fact, they have this locally Lipschitz at p property. We brought in the idea that linear transformations don't scale in an unbounded way. And probably the most interesting thing we did was work out the appropriate fancy zero to add inside of our norm. But if you have those steps handy, then this proof just turns into an algebraic triangle inequality exercise. I hope you enjoyed looking at this with me. Thank you for your attention.